Hello, welcome back to Earth Materials. Today I want to talk about sheet silicates and amphiboles, so their structure and chemistry. This is an example of an old lamp. These windows here are made out of the sheet silicate muscovite. So I want to talk about sheet silicate structure. We talk about two different structures, sandwich structure, bread and butter structure. A little bit about chemistry, trioctahedral versus dioctahedral. Something about serpentine structures, amphibole structures, and then how cleavages are reflective of how these structures work in amphiboles and micas. At the end of this, I hope students will be able to distinguish between different types of sheet silicates. So if I gave an image of a structure from, say, Vesta or another image, to be able to say something about what kind of sheet silicate it is, to be able to say something about chemistry of the different sheet silicates, to identify different serpentine structures, again from images, to relate chemistry and structure among amphiboles, sheet silicates, and pyroxenes, and to say something about why we see the cleavages that we do in pyroxenes and amphiboles. Okay, first let's talk about sheet silicates. So sheet silicates are particularly important for micas, for muscovite and biotite. And the way this structure works is there's a tetrahedral sheet, an octahedral sheet, and a tetrahedral sheet that are all bonded together. So we call this a TOT, and this is the sandwich structure. Sandwich because this is like a stiff piece of bread, sort of squishy octahedral sheet, another sheet of bread, and this forms the basic structure of a mica. Now, in between these sheets is a very large site which is occupied by an alkali cation, potassium, sodium, can be calcium, and this is what holds the sheets together. So we see this TOT structure with these octahedra electrostatically holding the sheets together. If we look down on these sheets, these are silica tetrahedral rings, all arranged into like a honeycomb structure into a big sheet. And then underneath it, we can see the octahedral sheet. This would be for biotite. Muscovite has the same kind of structure, silica tetrahedral sheet, octahedral sheet underneath it. But remember that aluminum, which is what occupies the octahedra in muscovite, has a charge of +3, whereas biotite has iron and magnesium in the octahedral sheet, has a charge of +2. And so what that means is that 1/3 of the octahedra in muscovite actually are empty. They have a vacancy to them. And so this gives rise to something that we call trioctahedral sheet silicates. Biotite is a trioctahedral mica, has 3 different octahedra all occupied, versus dioctahedral sheet silicates. Muscovite is a dioctahedral mica because only 2 of these 3 octahedra are occupied. So this gives us the TOT structure and a distinction between dioctahedral sheet silicates and trioctahedral sheet silicates. Now, one thing I'm going to point out as well about the octahedra in micas is, remember, the octahedra have certain pointing directions, and in micas, these octahedra all point in the same direction. So even though the sheets have this hexagonal symmetry, micas do not belong to the hexagonal crystal system because the C-axis is bent. It's at an angle to these sheets. Remember, in the hexagonal crystal system, the C-axis has to be perpendicular to the sheets, and because it isn't in micas, they all belong to the monoclinic crystal system. It does mean, however, that micas can have a sort of pseudo-hexagonal symmetry. You'll find sheets of micas that look like they're hexagons, but the C-axis is actually at an angle to those sheets. There's lots of chemical substitution. The alkali site can typically take potassium and sodium. It can also take calcium, a bunch of other cations in columns 1 and 2 on the periodic table. The octahedral sheet can have either 2 or 3 cations in it, dioctahedral, trioctahedral. Typically takes aluminum, magnesium, and iron, can take a whole bunch of other elements. The tetrahedral sheet pretty much is restricted to silicon and aluminum. There's a hydroxyl that's hanging off of here, and there are some fluor and chlor micas, so they have fluorine and chlorine. They're not really so common. These elements in black are the ones that make up most micas. Okay, so like I said before, you can have trioctahedral micas where all 3 octahedral sites are occupied, like phlogopite here. Or you can have dioctahedral micas where only 2 of these octahedra are occupied. Here's some common micas. Here's biotite, brown mica, anite, which is virtually black. It's the iron end member biotite. Phlogopite, magnesium end member biotite. And then here's muscovite, dioctahedral aluminum mica. And then there are various other less common micas. This one is margarite, this pink mica here. It's sort of like a calcium muscovite. Lepidolite is a lithium aluminum mica, and it's an important ore of lithium, actually. Paragonite is like a sodium muscovite. So you take muscovite and put sodium in the alkali site instead of potassium. And then clintonite is like you take biotite and you substitute calcium for potassium. So just like there's a calcium biotite called clintonite, there's a calcium muscovite, which is called margarite. Now, there are sheet silicates that are structurally a lot like micas, and 2 of the important ones are pyrophyllite and talc. Pyrophyllite has the same structure as muscovite, it just doesn't have an interlayer cation. So the composition is different. It's basically all aluminum in the octahedral sheet, all silicon in the tetrahedral sheet, but no cation to hold the sheets together. Talc is like biotite, iron and magnesium in the octahedral sheet, silicon in the tetrahedral sheet, but no interlayer cation to hold them together. And so these 2 minerals are held together not by electrostatic forces between the sheets with an interlayer cation, but by van der Waals forces. Of course, van der Waals forces are very weak, so these minerals are very, very soft. Talc, of course, is number 1 on the Mohs hardness scale. And so these are technically not micas. To be a mica, it has to have these TOT sheets that are held together with an interlayer cation. And because these don't have interlayer cations, we simply refer to them as sheet silicates, not micas. Okay, which of the following is not true about micas? And the answer is they are not double-chain silicates. So this would be an amphibole. We'll get to that later. They're sheet silicates. So at this point, I'd hope you'd be able to explain what the sandwich structure is. We haven't gotten to bread and butter, so let's not worry about that yet. But to say something about the sandwich structure, TOT structure, and then explain the difference between trioctahedral versus dioctahedral sheet silicates, and maybe give a couple of examples. Muscovite versus biotite, talc versus pyrophyllite. Okay, let's talk about serpentine minerals. Serpentine minerals have what's called a bread and butter structure. So remember, the sandwich structure has a tetrahedral sheet, octahedral sheet, tetrahedral sheet, TOT. Bread and butter has only a tetrahedral sheet and an octahedral sheet. So it's like bread with some squishy stuff on top. So here, for example, are the structures for chrysotile serpentine, lizardite serpentine, and antigerite serpentine. And you can see that they have tetrahedral sheets and octahedral sheets, but no tetrahedral sheet sitting up here. They're not micas or TOT structure. These sheets are held together with hydrogen bonds, with the exception of antigerite. There are hydrogen bonds in here, but there's also a direct connection between the sheets. Now, it turns out the way these sheets are put together, the points on the silica tetrahedra don't quite match up with the points on the octahedra. And so different serpentine polymorphs accommodate this mismatch in 3 different ways. Chrysotile simply bends the sheets. Now, if you bend the sheets in this direction, the points on the octahedra come closer together, and the points on the tetrahedra get farther apart, and they can link together. And so this gives rise to a sort of circular structure, and I'll show you what that looks like. Lizardite adds aluminum to the system. And when you add aluminum to the tetrahedral sheet, the points of the tetrahedra spread apart. And when you add aluminum to the octahedral sheet, the points on the octahedra get closer together. And so then the points can match up, and you can get these nice straight sheets. Antigerite is kind of weird. It bends in a particular direction, just like chrysotile does, and then it flips over and bends in the opposite direction. And so you end up with this bend and then flip and bend and flip and bend and flip and bend and flip. So that's what's shown here. Lizardite, you add aluminum. Chrysotile, they curve into spirals. And antigerite is bend and flip and bend and flip. So this, for example, is chrysotile asbestos, so serpentine asbestos. And these are transmission electron microscope images, and this shows these spirals. These are little spirals of these sheets. So here's a spiral that comes around, and you could trace it around and around and around and around and around, end up being one of these two little sheets. These are actually intertwined. These sheets make structures like drinking straws, and it's the little drinking straws that make these fibers of asbestos. This one then is antigerite. This is the bend and flip. So here's our silica tetrahedra, here's our octahedra, and here's a transmission electron microscope image. Here's it bends and then flips over, bends and then flips over, bends the opposite direction, and so on. Now, chlorite is another sheet silicate, but it's more complicated. It has this TOT structure, silica tetrahedra, iron magnesium octahedra, silica tetrahedra. So that part is like a mica. But instead of having only TOT structures to it, it has an intervening octahedral layer. So this is like brucite. So this is like a regular interstratification of TOT structure. This would be talc without an interlayer cation. It has like talc in here and brucite. So it's talc, brucite, talc, brucite, talc, brucite. There's a term that we use for this. It's called a polysomatic series, and it refers to regular interstratifications of these different units. So we can talk about talc, which is a TOT structure, and we can talk about brucite, which is just octahedra, octahedra, octahedral sheets. And then we can talk about chlorite, which is a regular interstratification of talc and brucite. So it's like talc, brucite, talc, brucite, talc, brucite. There are lots of other polysomatic series, but this is a really classic one. Okay, which of the following is not true about serpentine? So some of this we didn't really talk about. Are they trioctahedral sheet silicates? The answer is they do not have an interlayer cation. Yes, they are trioctahedral sheet silicates, and typically the octahedral and tetrahedral sheets have to deform to match up. That's true for 2 of the 3 serpentine polymorphs, and the sheets are held together with hydrogen bonds. Okay, so now I hope you have a better understanding of how serpentine minerals work. Okay, let's talk a bit about amphiboles. Amphiboles are quite complicated. They consist of double chains of silica tetrahedra. So these are the 2 chains of silica tetrahedra. You're looking at them from the side. So this is one going back and forth and back and forth and back and forth into the distance. Here's another one that goes back and forth into the distance. And so these 2 chains link up together to make a double chain. Here you're looking down on those chains. So here is one of the chains. Here is the other chain. And these link together to make these double chains. Now, one of the interesting things about amphiboles is that we can describe the center of this structure as being like a mica. So if you could extend these chains out in this direction, and you could extend these octahedra out in this direction, you would end up with a structure that looks a lot like a mica. So if you just cut that mica structure so you only have these 2 chains, then you get something that looks like the center of an amphibole. And on the side are octahedra that are very much like pyroxenes. And there are 2 of those. So if we take the center of this amphibole, it looks like a mica, and on the sides, it looks like pyroxenes in terms of chemistry. Now we can define this basic structure here as an I-beam structure, very similar to pyroxenes like we were talking about before, but it's a much wider structure than in pyroxenes. Why? Because it's a double chain, not a single chain. And so the way these fit together, the weaknesses, these wide areas in between the double chains have a different angle of weakness. So where the cleavages go is now not 90-90 as in pyroxenes. It has an angle that's approximately 120 degrees and 60 degrees. And that's simply because of the configuration of the wide I-beams and the weaknesses between the I-beams. So it is not only the structure of amphiboles that can be described as composed of micas plus pyroxenes, it's also true of their chemistry. So for example, if we take diopside, which has this composition, we take 2 of those, and we add talc. Okay, talc is not a mica, but it has a structure very similar to micas, like we've talked about. And you add these 2 together, then you get the mineral tremolite. Similarly, if you take enstatite, 2 pyroxenes, and talc, and you add them together, then you get the mineral amphipholite, the amphibole amphipholite. And if you really want to do a true mica, if you take 2 diopside and 1 phlogopite, so now this is magnesium end member biotite, and you add them together, you get a not so common amphibole called potassium edenite. Now, just like there are polysomatic series among sheet silicates, we can also describe a polysomatic series among pyroxenes, amphiboles, and micas. So if you can imagine, here's a pyroxene, which is just a little I-beam. Here's an amphibole, which is a double I-beam. We can expand this out. There's another mineral here, which is called Jim Thompsonite, named after Jim Thompson, which is a triple I-beam. And then it can get wider and wider and wider until eventually it's an infinite I-beam, and that's what a mica is. And then we can regularly interstratify these. So here, for example, is a pyroxene interlayered with an amphibole. Here is an amphibole interlayered with this Jim Thompsonite. And this gives rise to a bunch of different minerals. This is called chesterite from Chester, Vermont. Here is a close-up view of the Jim Thompsonite, 1, 2, 3 chains. And here's an image of what Jim Thompsonite looks like. Amphiboles have a lot of chemical complexity. They have an alkali site that's inherited from the mica substructure, so it takes sodium and potassium. It has these 2 sites over here, a larger octahedral site and a smaller octahedral site. These are inherited from the pyroxenes. And so like the pyroxenes, this larger octahedral site can take calcium, like in diopside, sodium, like in jadeite, another pyroxene, as well as iron and magnesium, like the orthopyroxenes. And then this smaller site can take iron and magnesium, like clinopyroxene, orthopyroxene, and aluminum, like jadeite. This intermediate octahedral site, there are 3 of these. This is inherited from the mica component, and it typically takes iron and magnesium and can also take some manganese. And then this tetrahedral site can take aluminum and silicon. Now, you remember back to pyroxenes, the octahedra in pyroxenes can all point in the same direction, and then we get the clinopyroxenes, or they can alternate direction, and then we get the orthopyroxenes. Well, the same is true of the amphiboles because they inherit their structure from the same pyroxenes. So if the octahedra all point in the same direction, we get clinoamphiboles. And if they point in opposite directions as we move up the structure, then we get the orthoamphiboles. So here are some examples of different amphiboles. Here's actinolite. This is a calcic amphibole. It is a clinoamphibole. Here's hornblende. It's very similar to actinolite, also a calcic amphibole, but has a lot of aluminum and sodium in it. Also a clinoamphibole. Here is amphipholite. So it's biotite in the middle, actinolite around that, amphipholite around that. This is an iron-magnesium amphibole, and it is an orthoamphibole. And then this mineral is gedrite. Gedrite is also an orthoamphibole, but it has a lot of sodium and aluminum in it. This now is glaucophane. Glaucophane is a sodium amphibole. Tremolite, calcium amphibole. And chrysotolite, this is a really dangerous asbestiform blue amphibole. It's similar to glaucophane, but it has a lot of ferric iron in it, and it forms these fibers. Okay, so which of the following is not true about amphiboles? And the answer is they do not have restricted chemistry. They have very complicated chemistry. That's what makes them so useful. Okay, so at this point, I would hope you'd be able to explain a little bit about amphibole structure and chemistry, how it relates to micas and pyroxenes, or TOT sheet silicates and pyroxenes, and then to say something about what the cleavage pattern in amphiboles looks like. All right, thanks.